llama.cpp is the engine running underneath almost every local AI tool you've used, and I put it through 6 setup steps to find out if the extra work is worth it. The biggest surprise, a 2008-era Core 2 Duo with 8 GB of DDR2 still pulls usable tokens per second, community reported at around 2, using the same build process you'd run on a brand new GPU rig. By the end of this video, you'll know exactly which of these 6 steps just work, and which ones hide a real gotcha. Step 1 is the foundation, and according to official docs, it's clean. Clone the canonical repo at ggml.org.llama.cpp, run kmake b build, then kmake r build config release, and your binaries land in build bin. Llama kalai m model osh egfa p hello in 128 gets you inference on the first try. This is pure C and C++. No Python runtime required for core inference, which is rare in this space. It's MIT licensed, sitting at over 126,000 stars and 22,000 forks, with roughly a 1-day release cadence. The gotcha. Backend flags differ by hardware. CUDA, Metal, HIP, Vulkan. Each needs its own flag, and getting it wrong fails silently on some setups. Build works. Picking the right flag is on you. I went through the official llama.cpp README, the build docs, the server docs, and community performance reports. Then ran the actual commands myself so you don't have to guess which flags matter. gguf is the native format here, bundling weights, metadata, and tokenizer into one file. Llama CLI AIF gemel org quen 3.50 part preguf pulls straight from Hugging Face, auto-caching through the llama cache variable. You can pin an exact quant with a colon, like q4 koshko m. Load a local file the same way, just point m at the path. One of the biggest problems I run into when using AI agents is turning their output into YouTube content I can actually use to market my product. That's why this video is sponsored by Subscriber, a tool that helps business owners connect their AI agents to YouTube and market their products without spending 10 hours every week creating content. You can connect Claude or ChatGPT directly to Subscriber. It then analyzes your business, website, and YouTube channel to help you create SEO-optimized video ideas, scripts, thumbnails, and even complete videos that actually match your brand. What I like most is that every week, Subscriber gives me a list of high-potential video ideas I can immediately execute, and it can even help edit videos for me, with or without my face, including videos like the one you're watching right now. It's easy to get started, and you can try Subscriber for free using the link in the description below. Now back to the video. Architecture mismatches fail with a clear error at load time, not a silent crash, which according to official docs is exactly how it should behave. The gotcha. The same model often ships as Q4KM, Q5KM, Q80, and F16. Same weights, very different size and quality trade-offs. Pick wrong and you're either wasting RAM or wasting accuracy. A Llama server and model.jguf, port 8081, and you've got a real OpenAI compatible server running locally, hitting V1 completions, V1 chat completions, and V1 embedding. Point continue, open web UI, or a custom app at that URL, and it just works, no code changes. It also ships a built-in web UI for browser chat, and there's an alternative pip installable server, llama.cpp Python, if you'd rather stay in Python. The gotcha, full OpenAI API parity isn't there. Tools, vision, JSON mode, all partial and version dependent. Treat it as a drop-in replacement for the basics, not a full clone. This is where llama.cpp earns its reputation. On a Core 2 Duo E8400 with 8 GB of DDR2, running Quen 3.5 at Q44KMM with EMLOC, sheet egg size 2NE48, TAL2 NGL0, community reported speed lands around 2 tokens per second. Usable for chat on hardware nearly 2 decades old. On an 8-core AMD chip with dual-channel 3200 MHz memory, 5 threads saturate the available bandwidth. Push to 8 or 9 threads and speed drops because this workload is memory bandwidth. Bound, not compute bound. OS level tuning helps too. Veeam swappiness return option and unlimited memlock avoids swap-induced freezes, community reported. And on 8 to 16 GB machines, stick to 7B or 8B models at Q4 instead of reaching for 70B. And stick with me because the last 5 tests are where this decision actually flips. The ingl flag controls exactly how much runs on GPU. ingl 0 is CPU only. ingl 10 splits 10 layers to GPU, the rest to CPU. ingl 1, 99 or 999 offloads everything if it fits. The server defaults to auto-fitting based on device memory. For VRAM math, Llama 3.18b at Q405km runs about 4.9 GB across 32 layers, roughly 153 KB per layer plus KV cache. Supported backends span CUDA, Metal, HIP, ROCm, Vulkan, and SYTL. The gotcha: there's no universal optimal NGL value. It's model times VRAM times quant, specific to your setup every time. Advanced MOE tuning, routing experts to CPU with AT XPS ASH CPU exists, but it's not beginner territory. That's your starting point for planning offload. A Llama quantize model f16.ggf model QAF.ggf QAR Kosh auto M is the documented path, and the payoff is real. 4-bit quantization drops a 14 GB requirement down to 4 GB. Kquants use blockwise quantization to preserve quality across Q4 coarse M, Q58KS, Q6K, and Q80. The standard performance test uses 128 tokens against an empty prompt at 2048 context. The gotcha: bump pre-dash up for more context and you're eating KV cache memory. On small machines, that context bump can tank your speed. Balance it, don't max it by default. That's a 7B model running on hardware that shouldn't be able to hold it. Across all 6 steps, llama.cpp works exactly as documented. Clean CMake build, 1 command. Hugging Face downloads, a genuine OpenAI compatible server, real speed on ancient hardware, fine-grained GPU control, and quantization that turns a 14 GB model into a 4 GB one. Here is where the second pick clearly pulls ahead. llama.cpp wins every single step in this guide, no split decision here. If you want full control and maximum performance on any hardware, from a Raspberry Pi to an A100, this is the engine because it's the actual core running underneath tools like Llama and LM Studio. The default path for most people: clone, build, download a Q4 GGUF, run a Llama server, point your tools at it. The pitch is that llama.cpp runs anywhere a C compiler runs, and technically that's true. What that pitch skips is that backend flags vary completely by hardware: CUDA, Metal, HIP, Vulkan, and picking the wrong one doesn't throw an error. It just fails silently, and you're left debugging a build that worked. If you're deciding whether to run llama.cpp directly or let a wrapper like Llama handle it for you, that comparison is coming next, and it might change which path you take.